Good evening, everyone. Firstly, thank you for giving me a slot to speak in this session of Lightning Talks at the NCSE staff meeting. I'm indeed honored. I'm presenting today the collaborative work between NCSE and Khalifa University. I'm affiliated to the KU along with my supervisor Dr. Kamran Khan, and our collaborators at NCSA are Professor Seep Kaurik and Dr. Dia Babuda. Today's talk comes under the broad topic of deep operator networks for nonlinear mechanics. As we know, deep learning networks are increasingly used as surrogates to computationally costly problems, be it mechanics or any other field. Now, what are surrogates? Anything which replaces the original but gives the same or close to same output as the original. Now, in mechanics, the most challenging part of a problem is its analysis, especially when the problem is put in with complex geometries, variable loadings, time-consuming solver like finite element analysis or computational fluid dynamics, and a nonlinear behavior, say material, geometry, or contact, or even worse, a combination of all of these. Now, surrogates like DL makes life much simpler when it models the entire package of difficulties. Now, how does it do it? It takes few of these difficult runs, collects them as a training data, learn with the DL algorithm, validate the model with the test set, and lo and behold, we have a surrogate solver. Now, which solves the same problem which the original solver would have done in days on a supercomputer. It does on in minutes or seconds on a very low profile computer. So some applications where surrogate DLs have been used are parameter studies while designing microstructure of cellular materials, sensitivity analysis of optimization, and or stress predictions. Now, in this work, one such DL surrogate that we have used is the deep operator network developed by the Lu et al. Which is motivated by universal approximation for operators. As the name suggests, this latest DL is capable of learning operators to data. What makes it interesting is also the fact that while all DL approaches requires some retraining for any modification in your input parameters like loads or boundary conditions or initial conditions or material properties, but deponents don't need that, and because they're learning operators, they resemble the solvers because solvers are basically ODE or PDE operators. Now, the architecture involves two networks. One is a branch network and the other one is the trunk network Y. Now, U is actually input sensors, that is all the input values, input parameters, and Y are the locations, which are node coordinates, where you would want the output, which is S. So, from the convolution of U and Y, we get a solution operator O, which we try to match with the S, which is the output operator. And so the training epochs just try to minimize this loss, and that is how this model is built. Now, this example is more clear from our paper from one of the applications we've used on a square plate which is subjected to some boundary condition and a set of parameters being the elastic and plastic properties, also the direction and magnitude of the loads, and also the sign of the loads. Now, with this set of parameters, we have like around 6 parameters. So we have U as 6 input parameters. Y would be our node coordinates, where we want the output of stresses. So von Mises stresses are our S. So the U being all the 6 values, Y being the node coordinates, and S being the von Mises stresses. So for this particular set of values, we can find that this similarity between the ground truth and the predicted deponent predicted contour is very, very similar. And also see the time. This is the important part, that it does it 4 orders faster than the actual solution time of the solver that we have used for generating the data. The same thing goes for complex geometry with a variable loading condition, which trying to make it even more difficult, but you can see the predicted deponent predicted is still as good and still with a good in good time. So let me stop now with acknowledgements to all our collaborators, all the research computing facility at both NCSE and KU. Thank you.